So in grade 10, one of your big labs you probably did was blast off. Yes. Was blast off, where you cut up the Alka-Seltzer and tried to make the reaction faster. So you've already been introduced to the general idea behind how to make a reaction faster. And some of these things are actually even common sense. If you want to have pasta for supper, you just don't put it in water and let it sit, right? You make the water boiling, you increase the temperature of the water to make the reaction, the cooking reaction, happen faster. What we're going to focus on this year is looking at what we call the collision theory, or how are particles colliding and making a reaction faster. So it's not good enough to say the temperature increase it. If you increase the temperature, it's going to make the reaction faster. We're now going to consider how or why, okay? It is still a theory, so it is difficult to stop a reaction as it's going along and really visualize definitively what's happening with the particles. So when you create a theory, then you're basing it on the observations that you've made. So we're going to talk about on the Monday when we come back in 6.6 about making a possible or reasonable mechanism suggestion for a system. But so you could by the end of this unit really even write your own steps like Hess's law, based on a few ideas or few criteria about how a mechanism should be considered reasonable. So some of these topics are weird to think about, but actually also make sense, using common sense. So it's a bit of both. So you need to, a reaction not just occur. So we talk about in grade 10, single displacement, metals displace metals, for example. Your teacher grade 10 teachers love to use the analogy of the dancing partners switching. And then in grade 11, we talk a little bit about the activity series of metals. Is a metal reactive enough to kick out another metal? So not all single displacement reactions will occur. Then we get into stoichiometry. Is there enough reactant to get a reaction to occur? And now we're considering, are the conditions correct for particles to collide? Do they collide at the correct orientation? So are they in the correct 3D configuration? And do they have enough energy to break the bonds in the other molecules? So we talked about last unit, every single time a reaction occurs and you break bonds, that requires energy. So, and then the rate of reaction is proportional to the number of collisions that occur each second. So when we do the calculation for reaction rate, it's going to be the change over a change in time. So it really relates well to calculus. And eventually, if you take calculus, if you have it now or you take it next year, take it next semester, whatever, then you will talk about area under a curve. We're going to look at curves today and how the derivative relates, like when you write it like, have you guys done this? Like stuff like that, yeah? So as a function of time, a rate of change, those of you that have taken functions will recognize like finding the average rate of change, instantaneous rate of change, those kinds of things. Okay, so this picture is the final one is in the notes. So I'm just going to go through it and you can see how it relates to what we did last unit. Okay, so this is just a potential energy diagram, reactants and the products. And we would have said that they require a certain amount of energy to go. So let's pretend like our reactants are white and black circles. So they have to come together and hit each other. And that makes a reaction occur. So if the collision is effective, does it have enough force? Are they in the correct 3D orientation? That is a part of the activation energy. How much energy is required for that reaction to go? And then, so let's say they start to hit each other. Maybe they're going to hit here. Okay? We don't really know. It's a theory. based on observations. Then the bonds start to break. So visually, now they're all dotted lines. And so at the top of the potential energy diagram is the substance that has the highest amount of energy, right? It's at the top of the peak, so we call that the activated complex. It's a transition state. Normally, what we did with Hess's law, stuff that was in the middle, the reactants and the products, we canceled it out, right? So it's not an overall reactant or product. So again, is it perfectly going to look like this? Well, that's our best guess, the best theory. And then they stop colliding and you get new products. So that is a potential energy diagram from last unit. We are going to switch to what we call Maxwell-Boltzmann, sorry. So here, this is not something we labeled last unit. The activated complex or transition state. So this down here is talking about trying to relate what happens with, is it endo or exothermic? So this is not a very big difference, right? However, it is exothermic. The products have released energy. But that was last unit. So we're going to shift and look more towards this. So the transition state occurs at the peak of the potential energy diagram when the reactants have formed the activated complex. So there is a variety of ways we are going to try to explain what happens with a molecule. So should you take organic chemistry, they talk a lot about what happens with carbon and the transition state in an organic reaction. There's a lot going on there. But for the most part, for most of chemistry, it is difficult to stop a reaction and say, oh, this is the transition state. Also, usually we don't really care. We don't want the transition state. We want the product to sell it. Maybe it's a precipitate, a gas, whatever, energy, whatever. However, we have to consider what's going on in the middle. So we're examining the transition or change from the reactants to the products. And we're going to focus more on kinetic energy. So in this unit, because kinetic energy is the energy of motion, and if particles are colliding, they have to be moving. So we are going to switch our focus to kinetic energy, but it's still going to follow the law of conservation of energy. You still can't get energy from nothing. So the activated complex is the chemical species that exists with partially broken, partially formed bonds. It is very unstable. It has the maximum potential energy possible. So again, it's found at the peak, at the top of the hill, whatever you like better. I guess that's... Okay, so let's switch and talk about the energy of the motion of the particles, or kinetic energy. So one of the ways that you can increase the rate of reactants is sort of out of your control. So the chemical nature of the reactants sort of implies like the chemical gods have decided some reactions are going to be faster than others. So we have already talked about this. Even in grade 9, some teachers talk a lot about trends in the periodic table, that if you have an alkali metal that's in that first column, then that means that they only have to lose one electron. That's very reactive. So sodium metal, which we talked about, it has to be stored in oil. It is so reactive, versus aluminum, which has to lose 3 electrons. You probably cook with aluminum. You keep it at room temperature. It's easily malleable, ductile. It is not going to damage your skin or anything like that. So, and we can't control that. That's already been decided. So that is the chemical nature of a reactant. A couple of the questions talk about the complexity of a molecule, which is a little bit later. So if you have a really big molecule and if it has to correctly collide at a certain spot, then the bigger the molecule, the more difficult that is. That kind of thing. That you can't control that. You can't make molecules smaller, right? Or compounds. So when you have a sample, then some of the particles are going to be moving quickly and some of the particles are going to be moving slowly. Again, none of them are going to be moving with 0 amounts of energy. I'm going to come back to this in a second. But what happens is you can build this sort of curve. So you can see here, it does not go to 0. So some particles are moving very slowly and some particles are moving very quickly. And this shape is called a normal distribution-ish, where you have a tail at the one extreme, like a little bit. Over here is a very high energy. Very few of them, very few molecules exist here. Most of them exist here, which would be around the average. So an unfortunate occurrence sometimes can be for students that not so much when it's regulated, like in our high schools, but when you go to university, you might hear more about the bell curve or the normal distribution that they try to actually skew test results and stuff to make sure that not a lot of kids are over here or over here. Most of them are in the middle. Really, from a pedagogical sort of standpoint, this is a terrible way to teach, but there are definitely, you'll even hear terms like bell up and bell down. Like if too many kids get low marks, they'll bell them up. Or if too many kids get high marks, they'll actually make the marks lower. Universities can do whatever they want. I can't do stuff like that, don't worry. But the reason, unfortunately, statistically, these sort of graphs become prevalent is because a lot of systems, whether it's chemical systems, student systems, whatever, can be applied to this sort of distribution. And that's where in a student sense, where the idea of standardized testing came from, because, we want most students to have an average amount of average amount of knowledge, which is a bit of a wacky way to think about it, but that was the prevalent idea for a long time. So Maxwell and Boltzmann were the first scientists to sort of be able to measure the particle energy, and they built that curve over and over and over again. So it is a valid distribution when you're talking about molecules. So just we'll write a couple things about a general Maxwell-Boltzmann distribution, because one of the things that students find a little bit frustrating is it kind of looks like a potential energy diagram, but it is very different, okay? Okay, so it is a closed system, so energy or particles are not getting in and out. It's like someone's taken a snapshot. So at this moment in time, how are the particles moving? And we're looking again at the energy of motion. How much kinetic energy do they have? Not potential. So the official definition for what we call threshold energy is the minimum kinetic energy required to convert the activation energy. So basically, the activation energy sort of implies potential. So to break the bonds, make the particles move faster, where simply, basically, because we're going to focus this unit on kinetic energy. So last unit, we would have said the activation energy was sort of the minimum amount. This one, we're going to call it threshold energy, is the minimum amount of kinetic energy required for particles to collide effectively. And we're going to use this terminology a lot. If particles are colliding effectively, that means that they are reacting. So if they're colliding effectively, they are reacting. If you prefer, you can write like a reaction is occurring. So there's a lot more to consider than just what we teach you in grade 10 about the type. I mean, that's important to get the background down, but now you know you can look up the activity series and how reactive a metal is. When you do double displacement, will they form a precipitate or not? You can also do that. And now another thing to consider as well is, do they have enough energy? So when we talk about the chemical nature of the reactant, it is difficult to change the chemical structure of an element, obviously, and make a reaction happen faster. So there are just some reactions that are naturally slow and some reactions that are much faster. And sometimes it makes a lot of sense. Like, for example, the reactions inside our body require what's called a catalyst or an enzyme to make them happen faster. So you can imagine that if your body instantly broke down proteins and stuff like that, then things could get out of control really quickly, right? So there are some reasons why we would want a reaction to go slower. The reaction of food rotting, for example, we can stifle that reaction or inhibit it by putting something in the fridge or adding salt to it. So there are lots of logical, common sense ways that we exploit these sort of concepts. Okay, so let's look at a Maxwell-Boltzmann distribution. So again, it's kinetic energy, and unfortunately, the kinetic energy now is on the horizontal or x-axis, and this is the number of molecules. So we have stopped, motioned, whatever, a reacting system, and we are looking at the particles at that moment in time. So some of the particles are moving with very little energy. Most of the particles are moving with this average amount of energy, and then a few of the particles are moving very quickly. So again, it's not to scale necessarily. If you prefer and you want to sort of add it in, you can think of this like a normal graph. Like here, this we call the origin, which is 0. Okay, and then let's say, I don't know, this is 50. We'll call it 50 kilojoules. Call this 100, 125. Okay, none of this, you do not need to draw them to scale, but if it helps you to think about what this means, then draw it in, okay? It's just like a normal sort of graph. Like this would be like maybe 1,000 particles, 2,000, 3,000, like it goes up like a normal graph would. Okay, so we already talked about what threshold means. So this picture's from your textbook, which is fine. The coloring here is a little bit wonky. I'm going to kind of fix it a little bit. But what they're trying to demonstrate here is how reactions can be different. Okay, so it says lower threshold and higher threshold. So let's just call this reaction 1. And I'm going to call this reaction number 2. So reaction 1 has a threshold energy at 100 kilojoules for pretend. Reaction number 2 has 125. So again, maybe reaction 1 has particles that are smaller, or has particles that only need to lose or gain a few electrons or whatever. So the chemical gods have decided what the threshold energy is going to be. That is not easy for us to change. But we're going to compare the speed, or how fast reaction 1 is, to reaction 2. But the thing, reaction 2 isn't so bad. That's like this would be reaction 2 over here. But reaction 1 is actually this and this, like all of this. You know what I mean? So I'm going to fix how they have colored it a bit, okay? So pick a color if you want. I'm going to use okay, so this reaction number 1, I have picked blue. You could pick whatever you want. So now this is the barrier. So these particles here all are past the threshold energy, or all of these particles, this area under the curve, they have enough kinetic energy to collide effectively. It is a ruthless sort of analogy in this at this point in your life. However, you can think of this like students, right? A barrier to get into university is set by the universities. We are going to take students who have an average of 85%. And everybody who doesn't have 85% does not get into that school. And people above will get an offer of acceptance. Okay, so and really that's where, you know, people systems can often be described by this normal bell curve distribution shape. So when you have a beaker or a vessel, some kind of vessel with a reacting system, there are some particles that are always going to be moving too slowly for whatever the minimum that is decided by the chemical nature of the reactants for a reaction to occur. So depending on this minimum, if it's lower, then more particles are going to be reacting, and if it's higher, there are going to be less. So these particles here, represented by this area, are never colliding effectively. They would just bump into each other, move away, and still be the same. So again, to sort of fix the coloring of this picture, I would pick another shape. So if you did lines like me, then make dots or something in between them past the line for reaction 2. So I'm going to truncate this one here because the same thing applies. Now, if this bothers you, then you could even add up here, like if you can't see in your head that reaction 1 is all the lines and you want to add this one up here, you can do that. Really what we want to emphasize, reaction 1 with the lower threshold has all these particles colliding effectively. Reaction 2 with the higher threshold only has these ones, okay? So decide what makes sense for you. So I want to show you what I wanted to show you how long it was. We're going to fill in the blanks, okay? So in the end, we need to take the idea about threshold energy and apply it to how fast is the reaction going to go. So if you think about it, if a reaction has more molecules colliding effectively, which means more reaction is occurring, is the reaction going to go faster? Yes, of course it is. So then you look at the curve, and whatever these are, whatever they've been decided to be, I've randomly just picked 100 and 125. It doesn't matter, right? One of them is lower or closer to 0. One of them is higher or farther from 0. You don't need the numbers either. So if a reaction has a lower threshold energy, then you can see that all of these particles, or this area under the curve, all of these particles are going to be considered colliding effectively. Whereas this reaction, only this many will be. So if you have more particles considered colliding effectively, are you going to be faster? Yeah. So reaction 1 has more molecules colliding effectively because it has a lower threshold energy. Therefore, reaction 1 would be faster. And again, it's an unfortunate analogy. However, if a school or a program has a lower barrier to get in, are more students going to get in? Yes, and less students will get in when there's a higher threshold. Okay, so some molecules or compounds have bonds that are relatively weak and a small activation energy. So we have talked about this in different ways. So in grade maybe 9, and especially for sure 11, you talk about trends in the periodic table. We even talked about it last unit, right, with the differences between the organic molecules. There are plenty of ways that the strength of the bond can be different. Even if you continue in pure sciences next year, you can even calculate the bond length or how long the bond is and how that can affect strength. So there's lots of ways to quantitatively figure out whether a bond is weak or not. So in this year, we're just going to use the general ideas. If you have a weak bond or a small activation energy barrier or threshold energy, they're essentially the same thing, then a larger fraction of molecules is able to collide effectively. And again, colliding effectively means reacting. So then if it's weak bond, low activation energy, low threshold energy, larger amount of molecules colliding effectively, then this would make the reaction faster. So because collision geometry, so that's like the correct orientation or correct 3D idea about a molecule or compound. So if you have something that's complicated, it's got a complicated molecular structure, complex ions. So one of the questions in the homework, I think, is like a simple metal cation and then a really complex polyatomic ion. So the more complex ion is going to be harder or less reactive because more bonds have to be broken. The chance of them colliding in the correct orientation is going to be less, and then the reaction will then be slower. And again, we as humans, we exploit these ideas. So if you think about things that we use on our bodies, what do we wear? Silver, platinum, gold. These are transition metals that are big and have that weird sea of electrons. So the chemical nature of those elements makes them less reactive. So what do? We wear them as jewelry. Nobody would be wearing sodium on their finger and expect things to go well. Okay, so we use these ideas all the time in a practical way for us, if you're into jewelry. Okay, so the next two, concentration and surface area, are much more logical, and these would be the ones that you guys used in grade 10 when you did that blast-off lab. So when you have a higher concentration of a reactant, then there is a greater number of particles per unit of volume, which are more likely to collide. Again, always make sure to bring it back to the collision. So let's say you could even think of it like us. If you go in the hall right now and walk around, there's a low concentration of students. Is there a chance that you're going to collide with somebody else? Probably not. Ring the bell, every single kid is in the hallway. Is there a greater chance that you're literally going to collide with someone? Yes, right? It happens all the time. So you can think of yourselves. So then again, depending on how far you go with pure sciences, you can calculate the probability of an effective collision based on the concentration. And then, so it is actually a direct relationship that you can mathematically figure out, but we need a little bit more calculus to do that. So those of you that are going to take like pure sciences, you'll be able to do that next year. Surface area. So again, we use this all the time when you're cooking, or you're trying to even a reaction, not a reaction, a physical change, like getting something to dissolve. You crush it up in order to get it to dissolve faster. So surface area only applies to heterogeneous reactions. So usually this means the one substance is usually gas, so gas and liquid or gas and solid. Usually not liquid and solid. That's not usually enough of a state change, but sometimes. So the greater the surface area of the reactants, which is weird to think of, but it relates to the size of the piece. So the more particles you have, the more surfaces you have available for collisions to occur. So again, the more surfaces that are available for contact, then the faster the reaction will go. So this example is using powdered zinc versus a chunk of zinc. If you have a piece of zinc, the only atoms on the outside that can come in contact with the acid. If you have powdered zinc, so now we have a solid, and hydrochloric acid, remember, has to be aqueous, so they are two different states. So if you use powdered zinc, many more zinc atoms collide with the acid molecules per second, so you're going to get a faster rate. Another super good example of this, not that I am telling you to do this, but you can, even something like flour. So in a piece of bread, if you put fire near, like a match or a lighter, near a piece of bread, is the bread going to ignite and explode? No. If you put flour in your hand and like a match, and you go like this and blow over it, it can actually ignite. Or if you ever go to a flour mill, they have to be really careful about friction and creating sparks, like you can actually get explosions. So that's another really good example of surface area. But again, things like this you would do without even thinking about the chemistry behind it. Now this year, you just want to make sure that you talk about the collisions. If you have more surfaces available for particles to collide, the reaction will be faster. Okay, and then the last one we're going to talk about today is temperature. So temperature, again, we cook using hot temperatures usually for this very reason. But temperature is going to have a very dramatic effect on reaction rate because it affects how often the particles collide and how much force there are. So it's really two reasons. Okay, so these are very fancy terms, the collision frequency. What does that mean? Causes molecules to collide more often. Okay, so more often and with more force. And again, you can think about this with yourself. If you're you're walking with somebody and you're trying to knock them off their course, if you're just walking beside them, then you're probably not going to. If you run at them and hit them with more force, the chance of you pushing them off their course is going to be much greater. Not that I am not encouraging you to do that, but. And temperature is a very popular way to make a reaction faster because it's easy to do. You can use a Bunsen burner to easily add heat. At your house, you can turn on the stove, right? No problem. You can even think of it like the reaction on food. So if you leave bread in sort of a hot, like a, say you have one of those like a spot in your kitchen, you always put the bread and it gets really hot in there because it's closed in. The bread might go moldy faster. Where could you put it to prevent the mold reaction? You could put it in the fridge because the fridge is cold. That's why we keep our fridge cold. Not just for bread, but other items as well, right? You can't leave milk on the counter and expect good things to happen, so it's going to go bad faster, right? Okay, so this picture now is a Maxwell-Boltzmann distribution at 2 temperatures. So if I think I posted it in color. If it didn't print in color, what I would do is go over it now so that you can see the difference, okay? So T1 is this blue line here. T2 is the green line. It doesn't have to be blue and green. They just chose those colors. You can do pencil and pen, like it doesn't matter. So this picture is a little bit different than our other Maxwell-Boltzmann distribution. Now what we have done is change the temperature. So it's the same number and type of particles, and also there's only one threshold energy, okay? So when you change the temperature, the threshold energy is not affected. Like the chemical gods deciding where that barrier isn't changed. Okay, so when you change the temperature, it doesn't change or lower. Usually we want the threshold to be lower to make the reaction faster. So it doesn't lower the threshold energy. And so it does 2 things, right? Changes how forceful a collision is and how often the collision occurs. Okay, so where were we? The temperature does not change the threshold energy. So we need to decide, is temperature 1 hotter or temperature number 2? So again, the shading of the picture, I don't love. It's not my favorite. So temperature 1 is my blue line, whatever color you made it. So a really, really high peak on the left side of the threshold, right? So these particles are not colliding effectively. They do not have the minimum amount. And then this very small area over here. So I don't know. I don't like the double green. I'm going to make it stand out more, okay? And maybe I'll use dots just like I did last time, okay? So this is how many particles, but also these ones down here as well, right? Or if you like curly Q brackets, you can do that too. Yes, Emma. Here? Yes. So temperature 2, the green line on my graph, is shorter here. The peak is not as high, but over here it is higher. So temperature 2 is all of the area under the green curve. So you do need to remember from last unit that temperature is a measure of the average kinetic energy. So the higher the temperature, the more kinetic energy. So if we have the temperature 1 and temperature 2, or the blue line and the green line, so here Temperature 1 is much higher here and then much lower over here. So remember, there is the same number and type of particles. So when you do calculus and area under the curve, you would be able to prove that the decrease in slope here is equivalent to the increase in the shape of the curve here, the area underneath. But for now, we're just going to do it visually, okay? So when you have either the curlicue or the dots and the lines and the dots, like this whole area here represents more molecules than this teeny tiny little sliver here, yes? So temperature 2 shows more molecules with higher kinetic energy, which are also, there's more of them past the threshold barrier, that goes without saying, goes together. So if you have more particles with higher kinetic energy, they're going to be moving faster and colliding faster, which means a faster reaction. So higher temperature, because more of them are moving faster, which means in the end is going to be a faster reaction. So unlike surface area and concentration, which would not affect the kinetic energy or the shape of the curve, temperature has a much dramatic effect on the rate of reaction because it affects how fast they are moving, so how hard they collide, and how often. So when you guys did that blast off lab, did you have to compare? Like if you pick surface area and temperature, did you have to make a graph or did you just pick one? Do you remember? He should make you do two and see which one's faster. So this is basically saying the same thing. And again, you're eventually, if you continue with math and science, you're going to be able to calculate the area under the curve, and the areas under the curve would be equivalent, like we're not creating more particles. So temperature 2 has more molecules with sufficient energy, so that reaction would be faster. And it's actually, sometimes you'll hear the term Q10, so again, you can quantify, if you change the temperature by 10 degrees Celsius, it usually doubles the rate of reaction. So, sorry if I went too fast there. So what I'm going to do, I'll erase what Mr. Zemon wrote and I'll write down the homework. It's on D2L as well. And then the grade 12 break is 10:35, so at 10:40 I'll start 6.1. It's a little bit more straightforward, especially those of you that have already taken functions. It's less theoretical.